Now that we spent a bit of time going through taking derivatives, seeing what those mean in terms of the graph of a function, we're going to combine that together to just talk about a summary for curve sketching. So pretty much what you should be going through to get a really good visualization about a function and figure out all the key components to be able to graph it nicely. So we're going to go through a bunch of different guidelines, and then pretty much we're going to do just a couple examples because you're going to see these do take a little bit of time. So first and foremost, when you're starting with any function, you need to find its domain. Where does it even make sense to test? Where does it even make sense to find increasing and decreasing? You want to find the values of x for which the function is defined. Then, if you can, you want to find your different intercepts because those are always going to be good pieces to graph. So the y-intercept is going to be you plug in x equals 0. To find the x-intercept, you're going to set the function equal to 0. You really only want to do this if the intercepts exist and they're not insanely difficult to solve for. Third, you should always test for symmetry because that can save you a ton of time. So going back to our college algebra days and pre-calc, you evaluate a function at negative x. If that minus sign disappears for all x in your domain, then we say f is an even function. And that curve's going to have symmetry about the y-axis. So really, I only need to graph half, and I know exactly what the other half will look like. Likewise, if you evaluate your function at negative x and the minus sign pops out, then f is an odd function, and you have symmetry about the origin. The third type of symmetry is specific to a lot of our trig functions, and it's basically going to be if you take your function and you add this quantity p, you're going to get the same output for all x in your domain. This is called a periodic function, and the ones you can think of, your sine, cosine, tangent, all of those are periodic. For sine and cosine, if you add 2 pi on the inside, that would take you once around the unit circle, so you have the same visual over and over and over and over again. So for all of these, for our first case, if you have an even function, you really only need to graph half, and then to get the other half, you just reflect about the y-axis. When you have an odd function like y equals x cubed, you just need to graph half the function and then you're going to rotate it 180 degrees, or think about flipping it over the x and then over the y again. Finally, if you have a periodic function, all you need to do is graph it over one period, and then you really just get to copy and paste it from there. Okay. After you've gone through and found the symmetry, then you want to move on and figure out any asymptotes for your function. First one we learned about were vertical asymptotes, and that is a vertical line that your graph is going to hug. So basically, if you approach from the left or right-hand side, it's going to blow up to one of these infinities. And so you do actually want to calculate these limits because those are going to be really helpful for graphing. So knowing that when you approach from the right, it goes to positive infinity is really useful information. After that, you want to figure out your horizontal asymptotes. So remember, now you're going to let x approach positive and negative infinity. If those limits exist and equal some quantity L, then y equals L is a horizontal asymptote. Now, if you find out that this limit doesn't exist, you might still find out it goes to positive or negative infinity. So either way, by calculating these limits, you're going to have useful information for sketching. Okay. After that, now we can use all the applications of derivatives. So we can find where the function is increasing or decreasing by basically figuring out where that first derivative is positive or negative. With that, you can then find your local max and min values. So you find those critical numbers, and then you can use the first or second derivative to determine if they're maxes or mins. And really, you can kind of do these steps simultaneously because you're going to figure out where it's positive, where it's negative. You'll have those nice little charts. Immediately, you're going to know maxes or mins. Then finally, you can find your concavity, so you know which way the curve is going to face. You're going to find that second derivative and figure out where it's concave up and concave down, and that's going to tell you if there are any inflection points, and that's specifically where it changes concavity. After you've done all of this, then you can finally get a good sketch using all of this information. Okay. So let's try an example together. Let's sketch the graph of this particular function, which is x squared divided by the square root of x plus 1. So first and foremost, we want to go through the domain. We've got a square root, so I definitely need what's under the radical to be greater than or equal to 0. But I can't divide by 0, so I don't need to put an equal to sign under here. So solving for this, that tells me my x needs to be greater than -1. So my domain is from -1 to positive infinity. Now I can go find my intercepts. So I'll start with our x-intercept. You're going to set that function equal to 0. So you can go ahead and multiply by this quantity in the bottom. This is the same thing as figuring out where does x squared equal 0, and that only happens when x equals 0. So our x-intercept is going to be the origin. For our y-intercept, you plug in 0. So you're going to get 0 squared over the square root of 0 plus 1. And so our y-intercept is also the origin. Okay. Now third, we go on to symmetry. So I want to evaluate my function at -x. So anywhere I see an x in here, it gets replaced by -x. So I've got -x squared over the square root of -x plus 1. In the numerator, that cancels, but the denominator, nothing happens. So really, this isn't my original function, and also I don't have a minus sign pop out. So really, I have no symmetry for this graph. So next, we move on and find our asymptotes. So we're dealing with this particular function. First and foremost, remember our domain is from -1 to infinity. For that vertical asymptote, that's going to be where does our function approach positive or negative infinity. And remember, back to all of our other days, that's going to be when you divide by 0. So thinking about this, if I plug in -1, that's going to cause 0 in the denominator. So I want to figure out which infinity I'm going to possibly approach. And so we've got to think about taking a limit as we approach -1. The problem is I cannot approach from the left-hand side because my function is undefined to the left of -1. So I'm really only going to take the limit from the right. So for my vertical asymptote, I want to look at the limit as x approaches -1 from the right of our function. And so we need to figure out just in our head really what's going on. So if you think of the numerator, that's going to be approaching -1 squared. So the numerator is approaching +1 as x approaches -1 from the left. The denominator is approaching 0. You get the square root of -1 plus 1 as you approach -1 from the right. But because you're approaching from the right, that's numbers like -0.9, -0.99. So inside, you're going to have the square root of a positive number. So it's going to be approaching 0, but it's small and positive. So ultimately, we're going to be approaching positive infinity from the right-hand side of -1. So immediately now I know x equals -1 is a vertical asymptote. Next, we find horizontal asymptotes. So we need to calculate two limits as x approaches positive or negative infinity. But thinking to that domain, this one is completely useless for us because x has to be greater than -1. So this limit isn't possible from our domain. So we really only need to take the limit as x approaches positive infinity for this function. Remember the approaches, we're going to multiply top and bottom by the highest power in the denominator, which for us is the square root of x. So what that causes is x squared divided by x to the 1/2 in the numerator. And we've got the square root of x plus 1 divided by x in the denominator. So simplifying this, we're going to get x to the 3/2 in the top. And in the bottom, that's going to simplify really nicely to 1 plus 1 over x. This is going to go to 0 as x goes to positive infinity, but the numerator is just getting larger and larger. So overall, this goes to positive infinity, which means we have no horizontal asymptote. But again, this is useful information for us. So we know we should always be heading in the positive direction and going up, up, up. Okay. Next, we go on to increasing and decreasing, and then that will tell us what our max and min values are. So we're working with this particular function. We need to go ahead, take a derivative, see where that derivative is positive or negative. So we're going to go through this relatively slowly. We've got to use our quotient rule. So we get low d high minus high, and then we want to take the derivative of the low and then divide this by low. So that's x plus 1 to the 1/2 squared. Okay. So the derivative of x squared is going to be 2x. The derivative of this thing is we bring that power down, we decrease it by 1, so our new exponent's going to be negative 1/2. And then technically you should say by chain rule, the derivative of the inside is 1. But I'm going to ignore that for now since we know it's just 1. And then luckily in the bottom, we're just going to get x plus 1 because that square and square root are going to cancel. Okay. So unfortunately, I am going to have to see where this thing equals 0, and I'm going to have to see where this thing is undefined. So we've got a bit of an issue because this form is not really conducive. So I am going to have to simplify. So I want to rewrite these radicals, or these exponents with radicals. And here we're going to have x squared in the numerator. We have a 2 in the denominator, and that square root is going to move to the denominator as well. And then this whole thing is divided by technically x plus 1, and I'll write it as the first power. I want to get this as a nice fraction over a nice fraction. Problem is I've got a fraction in my numerator. So what I'm going to do is I want to wipe this denominator by multiplying the top by 2 square root of x plus 1. And what we do in the top, we have to do in the bottom as well. So we go ahead and multiply everything out. This is going to give us 2x square root of x plus 1. That gets multiplied by 2 square root of x plus 1. Then that fraction is going to disappear. In the bottom, we're going to get 2 times the square root of x plus 1 times x plus 1. Again, consider that to the first power. Okay. So multiplying this out, we're going to get 4x. You get the square root of x plus 1 times the square root of x plus 1. That just becomes x plus 1 minus x squared. And in the bottom, you can condense those because it's the same thing. You add the exponents. The square root you can think of as x plus 1 to the 1/2. So we're going to get 3/2 in the bottom. Okay. So simplifying that out, this will give us 4x squared plus 4x minus x squared divided by 2 times x plus 1 to the 3/2. So one last step to simplify. This is 3x squared plus 4x divided by 2 times x plus 1 to the 3/2. So now we've got a nice format for our first derivative. We can now find our critical numbers. So this is going to be where this numerator is equal to 0. And so we can factor out an x to give us 3x plus 4 times x equals 0. So either x equals 0 or 3x plus 4 is 0. That's 3x is negative 4 or x is negative 4 over 3. And then we also want to see where our denominator is equal to 0. And that really is only going to happen when x equals -1. But going back, we only care about numbers greater than 1. So these are not in the domain. Which starts at -1 and goes to positive infinity. So really I have a single critical number, which is going to be 0. So we want to do our interval testing for our derivative, which again is 3x squared plus 4x divided by 2, x plus 1 to the 3/2. My only important number is 0. I'm also going to make a note that I cannot go lower than -1 because of the domain of my function. So I really have 2 intervals to test, but for that first interval, we have particular values that we can plug in. Okay, so I can't plug in -2 because that's going to cause me an issue in that denominator with that radical. So I have to pick something between -1 and 1. I'll pick -1/3. Purely because when we plug this into the derivative, you can use either format, which you can factor out that x. Because by plugging in -1/3, it's going to cancel with that 3 in the second component nicely. So we get x, 3 times -1/3 plus 4 divided by 2, -1/3 plus 1 to the 3/2 in the bottom. So that's -1/3 times -1 plus 4 in the numerator. And then 2 times 2/3 to the 3/2 in the denominator. So this is -1/3 times +3 over a positive times a positive number. So overall, I don't care what this number is, I just know it's negative, and immediately that tells us we're decreasing on this interval. So our derivative is negative, which means this is decreasing. Now I want to pick something from interval 2. And here you can pick +1 that falls in the interval. So if we plug this into our derivative, again, either form is fine. I'll use the first form. You'll get the same thing regardless though. In the numerator, we're going to get 3 plus 4. In the denominator, we're going to get 2 times 2 to the 3/2. Don't care what that is. I just know all those signs are positive. So it is definitely positive here, which immediately tells me my function is increasing. And now I get to classify this as a local minimum because we're making that shape where we switch from decreasing to increasing. Okay. So now I know my function is going to be increasing from 0 to positive infinity, decreasing on the interval from -1 to 0. And then we have a local min at 0, and my original function evaluated at 0, which we've already plugged that in. If you plug 0 back in all the way up here, you get 0. So we have a local min at the origin. Okay. So we are almost ready to graph. We just have concavity left. And so you'd have to take another derivative of this function. You're going to have to go through the same simplification process. So I'm going to go ahead and just tell you that the second derivative is going to be 3x squared plus 8x plus 8. divided by 4 times x plus 1 to the 5/2. So you'd pretty much go through the same thing of going through quotient rule. You'd have to simplify it in a similar process by multiplying by something to get rid of those square roots. Okay. But now that we have the second derivative, we need important numbers to do our interval testing. And so this is going to be where that numerator, 3x squared plus 8x plus 8 equals 0, or where the denominator is equal to 0. And this one's a little bit straightforward to solve because we've done it. It's x equals -1. But again, not important for us because this is not in the domain. To solve this one, unfortunately, you're going to have to use the quadratic formula. So you get -b plus or minus the square root of b squared minus 4ac all over 2a. And so if you go through that process, this is going to be -8 plus or minus the square root of -32 over 6. And so there are no real numbers where the numerator equals 0. So these are imaginary numbers. So the numerator never equals 0. Okay. So our numerator never equals 0. Our denominator doesn't have any problematic values that are in the domain. So pretty much what happens is when I do this testing, it's never going to change signs. Okay. So I only care what happens from -1 onward, and there were no important numbers anywhere else. So I have a single critical value to test. And so you can pick anything that falls inside this interval. 0 is probably the nicest one. So if we plug this into our derivative, way back up here, you're just going to get 8 in the numerator. In the denominator, you're going to get 4 times 1 to the 5/2. So this is definitely positive, which means our second derivative is always positive. And so our graph of f is concave up on the entire domain. From -1 to positive infinity. And so immediately you have no inflection points because your graph does not change concavity. Okay. We are finally at the point now we get to sketch by putting all of this information in one chart. First, we know we have a vertical asymptote at x equals -1. We know we go through the origin and that this point is a local min. I have to be concave up the entire time. We're going to be decreasing in this interval, increasing afterwards, always concave up, and I know that I'm approaching positive infinity on both ends, and I have 0 symmetry. So this is a decent graph of our function. So we're just going to try one more, so you can see it is tedious. We are going to start with the graph of f of x equals x squared divided by x squared plus 9. So we need to first find the domain. Then we want to exclude values that cause us to divide by 0. So I need to see, where does x squared plus 9 equal 0? Same thing as figuring out x squared equals negative 9, which gives you plus or minus the square root of negative 9. And that's imaginary numbers, so we really have no problematic x values. So you can plug whatever you want into this function. Your domain is all real numbers. Now we want to find our intercepts, so we need to find our x-intercept by setting this thing equal to 0. That's the same thing as solving where x squared equals 0. And just like in the last problem, your x-intercept is 0, 0. Your y-intercept, if you plug in 0, you get 0. Again, the origin is one important point for us. For symmetry, if I go ahead and plug in negative x, we're going to get negative x squared over negative x squared plus 9. In both those cases, the minus signs disappear, and you get exactly the same function back. So ultimately, f is an even function, and I know it's going to have y-axis symmetry. So when I graph this, it better look symmetric to the y-axis. For our asymptotes, remember our vertical asymptotes are going to be where we end up dividing by 0, but we already know that doesn't happen, so we have none. When we go to find horizontal asymptotes, we want to take the limit as x approaches positive infinity of our function, which really is a nice polynomial over polynomial. Divide top and bottom by the highest power. So in the numerator, you're just going to get 1. In the denominator, 1 plus 9 over x squared. This goes to 0, so you get 1 over 1. This limit is equal to 1. So y equals 0 is our horizontal asymptote that we're going to hug. If you do negative infinity, not going to change this bit at all. That second piece is still going to go to 0. So really, y equals 1 is the only horizontal asymptote. Okay. Now we want to get into increasing and decreasing and find any max and min values. So we need to take a derivative. And again, got to use quotient rule. So we get low d high minus high d low all over low low. So taking these derivatives, this is x squared plus 9 times 2x minus x squared times 2x over x squared plus 9 squared. So we do want to distribute that out. That's 2x cubed plus 18x minus 2x cubed. And then the denominator stays untouched. But nice stuff happens. Those disappear. And we get 18x divided by x squared plus 9 squared. So we have to find our critical numbers. This is going to be where our numerator equals 0. So 0 is an important point. Or the denominator is equal to 0, which again, that doesn't happen. So I really have a single critical value that I need to test, which is 0. And I want to see is my derivative positive or negative on each of these intervals. Okay. So from interval 1, we could pick -1. If I plug in -1 into my derivative, that's going to be 18 times -1 divided by -1 squared plus 9 squared. So -18 in the numerator and really 1 plus 9 squared in the denominator. So overall, definitely going to be negative, which means this function is decreasing. If I pick something from interval 2, we can pick positive 1. And so if I plug that in, we'll get 18 times positive 1 over 1 squared plus 9 squared. Don't care, everything's positive. So this is positive, and immediately this is increasing. So it happens to be, again, that this is a local minimum. Okay. So our function is decreasing from negative infinity to 0, increasing from 0 to positive infinity, and we have a local min at 0, and then the y value corresponding to 0, which again happens to be our origin. Okay. Now we'll go through concavity. So we've got to take another derivative, which this time I will indeed go through. We get the low function derivative of the high minus the high function derivative of the low. Okay. So this gives us x squared plus 9 squared. Derivative of the high is 18 minus 18x. And then derivative of this, we have to bring the 2 down, decrease the power by 1, and then that becomes the first power. But chain rule, we've got to take the derivative of the inside, which is 2x. So this is by our chain rule. And then this whole thing is divided by our denominator squared, which I forgot to do in the step above because I got eager and went to taking derivatives. So this is divided by the denominator squared. Okay. So we do have to simplify this a little bit if we can. This is 18 times x squared plus 9 squared. Minus, we got a ton of stuff. I'm going to leave the 18 untouched for now. We've got an x times x to give us x squared. And then we've got this 2 times 2, which is going to be a 4. And then I've got x squared plus 9 to the first power. This is all divided by x squared plus 9 to the 4th. So you have a couple ways of going about this, but everything has this x squared plus 9. The most I have is 1. So one of these can cancel. This will disappear, and we'll be left with 3 in the denominator. We can also take out an 18, so I'm going to save that for the next step. I'm left with x squared plus 9 minus 18 times 4x squared divided by x squared plus 9 to the 3rd. Factoring out that 18 will give us x squared plus 9 minus 4x squared over x squared plus 9 to the 3rd. Okay. And then we can simplify. This will give us negative 3x squared plus 9 in the numerator. And then one last step, I can take out a negative 3 to make my life a little easier, to give us x squared minus 3. Okay. And so we've got some important numbers. This is going to be where the numerator equals 0. So that's really just going to be where x squared minus 3 is 0. or where the denominator is 0. But again, that doesn't happen. So really, this is just where x squared equals 3, or x equals plus or minus square root of 3. So don't forget, when you take a square root, you get a plus or minus. Okay. So we need to test concavity with our second derivative, which is negative 3 times 18 times x squared minus 3 over x squared plus 9 to the third. And we have two important numbers, negative root 3, positive root 3, no values we have to exclude from the domain. So we have 3 intervals to test concavity for. So if I look at interval 1, negative root 3 is like negative 1.4. So I can pick negative 2. Plugging that into our second derivative will give us negative 3 times 18. Negative 2 squared will be positive 4 minus 3 divided by negative 2 squared plus 9 cubed. So this is positive, this is positive, this is positive, that's negative. Overall, this thing is negative. So immediately my graph is going to be concave down on this interval. If we pick something from interval 2, 0 is a good choice. Plugging that into our derivative will give us negative 3 times positive 18. 0 squared minus 3 is negative 3 over 0 squared plus 9 cubed. Those minus minus cancel, so this is going to end up being positive, and immediately that tells me my graph is concave up. So I know this will correspond now to an inflection point. Okay. I've got one last interval to test, and I will pick positive 2. Plugging that into our second derivative will be negative 3 times 18. 2 squared is 4 minus 3. In the bottom, we'll get 4 plus 9 cubed again. So I really get the same thing. This thing is going to be overall negative. And so we are concave down on this interval, and x equals root 3 is also going to correspond to an inflection point. So our graph is going to be concave down from negative infinity to negative root 3, and then positive root 3 to infinity. And it's concave up between negative root 3 and positive root 3. So we have 2 inflection points. The first one's at negative root 3, and then the y value corresponding to negative root 3. So if you plug that in, you're going to see your y value is positive 1/4. And then positive root 3, the y value corresponding to positive root 3 as well, is an inflection point, which because of the symmetry, this is also positive 1/4. So now we can go ahead and we can sketch the graph of our function. Doing the best we can. We figured out y equals 1 is a horizontal asymptote, and we are going to hug this on both sides because we got that symmetry. Our graph should be decreasing over here, increasing over here. We have an inflection point at root 3, 1/4, which is roughly around here. And then negative root 3, positive 1/4, roughly around here. Okay. On these sides, our graph should be concave down. So I need to hug that asymptote and have the curve down shape on both sides. We go through 0, 0, which is a local min, and in between here, our graph is concave up. So there is a rough sketch of what our graph of this function looks like. Okay. So take your time going through these. Make sure you're finding a lot of those key points. Obviously, if time is an issue, you don't have to find every single thing, but you definitely want to find some of those core components involving the first and second derivative.